Okay, so let's now talk a bit more specifically about electrochemistry. So in particular, we're interested in instances where we have both a chemical reaction going on and uh, some kind of electricity generation or motion of electrons. So we know that chemical reactions often involve loss or gain of electrons. And loss of electrons is referred to as oxidation. And we say that the oxidation number has increased when a particular complex has lost an electron, and gaining electrons is counterintuitively known as reduction. And we say in that case that oxidation number has decreased. Okay, so when we think about this, the context is that we're often thinking about a chemical reaction in which oxygen is playing some role, and we know oxygen is often found in its ionic state, so O2 minus, where the oxygen in solution often has a -2 valency state. So it has an oxidation number of -2. Okay, so a particular example, well, not a particular example, but a generic kind of example of what typically goes on in electrochemistry is that we have something like some element A that's oxidized. So it's in solution, let's say, and it's brought in contact with some other element B, and then what goes on is that we have interconversion between this and B going into solution, so B becoming oxidized and precipitating A. So what happens when we do that? Well, we can think about this in terms of the where the electrons are. So initially, if the oxygen is 2 minus, right, this is in a 2 plus oxidation state so that it's neutral, and here B is neutral. So what's happening is the electrons are moving from B to A. In order for B to have a 2 plus oxidation state and A to be electronically neutral. So in this case, we would say that A is reduced and B is oxidized, particularly for this reaction. Okay. Now, we can rewrite this. One way to simplify the problem, or at least to look more specifically at the part of the problem we're interested in, is to rewrite this ignoring the oxygen. So we can rewrite ignoring oxygen. And then we get the reaction would look like A2 plus B goes to A plus B2 plus, right? Or we can write this as half reactions. That is, we could explicitly say, well, what's going on is that we have A2 plus that's combining with 2 electrons that have been stolen from the B to create A, and we have B, which is losing 2 electrons to become B2 plus. Right? All of those are equivalent ways of talking about the same process, but here we're writing them in terms of two half reactions. So when we think about this schematically, what's going on, we could draw this as a diagram. So we could say over here we have A, which is in contact with A in, let's say, in solution with oxygen. And then we bring that into contact with B, which is in contact with B in solution, so B, the oxide of B. And then in order for this reaction to proceed, right, electrons have to go from B to A, right, in order to go this way in the reaction. So we would have an electron flow this way. And we would have to have an ion flow where the oxygen is moving from the A to the B, right? So we have to have O2 minus. So this is, on this side, we have electron flow. And on this side, we have ion flow, right? So by convention, this side is known as the anode. And this is where we're seeing oxidation. And this side is the cathode. And this is where we're seeing reduction. Okay. So this is now a picture of essentially an electrochemical cell. So what's happening? So two electrons are leaving a B atom, right? And they're flowing through the wire to the A tank, right? Where they're combining with an A in solution to precipitate neutral A, right? And releasing an ion. And the oxygen ion has to flow into the B tank and combine with the B ion that was released in the initial reaction. So this is known as an electrochemical reaction. Okay. And the way it would actually be realized is by taking a tank. So we would have some kind of tank here. Let's draw that in black. And we would fill the tank up with some electrolyte. Which is just basically some kind of solution. And then inside we would put some B and some A. Let's use the same colors here. And then here we would have our electrolyte surrounding that in blue. Okay. And then we would hook a wire from B to A. So we'd have a wire. And we know that electrons would be flowing from B to A. So this would be a negative pole and this would be a positive pole. And ions would be flowing in the opposite direction, right? So ions would be, in solution, we would be interconverting ions between AO and BO, which are both floating around in the solution. Okay. So this kind of setup is known as a galvanic cell. Or we could imagine running it in reverse, right? So this, so in the case where it runs spontaneously, so the galvanic cell runs spontaneously, but we could also apply EMF, a battery, put a battery across this and make it run backwards and make the reaction go in reverse. So a galvanic cell run in reverse is known as an electrolytic cell. Okay. And we'll talk about examples of both in a moment. And the electron flux through the external circuit is balanced by the ion flux in the electrolyte, right? So let's also note that.